Biological validation. So the first experiment we ran was the biocompatibility test. We did so using the Welsh t-test to compare PLA growth, screw growth, and control growth. And we noticed that p-values are all above 0.05. Therefore, it shows no statistical significant difference in growth rate.
So similarly to what Mathias said, we did an experiment using LED light strips where the light intensity was 115 microeinsteins, whereas the lights in the lab was between 160 and 200 microeinsteins. And we saw that the p-value was greater than 0.05, therefore we can have the same conclusion as the earlier results. Using the LED light strips, we saw that the overall algae growth rate is 0.71 cells per milliliter per day.
Finally, using the data from group 10 and group 9, we are able to predict how much ammonia is going to be excreted from our muscles depending on their weight. So using this graph, we found that in total we would have 0.186 per million ammonia excreted from our muscles.
Here's our demo of our feeding algorithm. This would be the algae bucket, and this is the muscle bucket. We have the OD sensor in this tube, the siphon that would feed the muscles, and this tube is connected to the pump that will move the feces to the algae to feed them. Now we're going to close the vault bag to get an accurate OD reading and run our algorithm. So we start it, and we see that the pump will be on for 18 seconds. So if we reopen the vault bag, we see that the pump is currently working. And then how this works is the algorithm calculates how much time the pump has to be on to supply the wanted concentration in the muscle bucket. This is we select a range we want to keep. So here we put a range between 1,000 and 1,200 moles per milliliter. Then we see after 18 seconds the pump's turned off, and we'll check again in around 2 minutes. This number is calculated by the algorithm that simulates the muscles eating the algae, and it will tell us how much time it takes for the muscles to bring back the concentration in their bucket at the lower end of the range that we want to keep. And then the algorithm will run again and feed them. As you can see, the pump has stopped.
So we tried different resistances on the light sensor and on the LED, and we ended up by picking a dark tape to put over the LED to avoid maxing out the sensor.
So in the experiment, we calibrated our OD sensor by starting off with measuring the clear water, and then we added more and more algae concentration, and we obtained a blank value of 725. And as you can see in the plot, it shows a negative linear relationship between the light sensor value and the concentration.
Finally, we want to prove the accuracy of our model, which we did by taking a sample and measuring the OD value of it and obtaining the concentration from that, which we then compared to the concentration value we received from the lab using the particle counter. This confirmed our accuracy of the whole setup. We also made sure to write our code in an object-oriented manner.
This is our muscle bucket. It has a fishnet that holds the different muscles and also a funnel that collects all the feces. This is the algae tank that holds the OD sensor that is covered by a pool noodle. We have tested the biocompatibility of the PLA of the funnel, the polyethylene of the pool noodle, and as well of the material of the weights. Then they have LEDs at the top that are connected to a programmable plug that will turn on and turn off the LEDs at the desired time. Everything is held in a bulk bag that we have measured the thermal efficiency. As we can see from the graphs, the bucket inside the bulk bag decreases the temperature slower than the one outside with no isolation.
Here's our automated cooling system for maintaining optimal water temperature for the muscle bucket. We constantly circulate water from the bucket through a cooling module using the 3 to 6 motor pump, and this prevents fouling and ensures continuous temperature control. Cooling is handled by the filtering model, which is switched on and off based on the readings from the temperature sensor that checks the real-time temperature inside of the bucket and feeds the data to the control algorithm. The core logic that we have is a PID controller. This update function calculates the difference between the target temperature and the actual temperature, which is the error, and that uses that compute to control the signal. Every 30 seconds, the system updates. The PID value is scaled using these PID parameters to decide how long the filter should stay on or off within that window of 30 seconds. We log temperature and PID values at every cycle, helping us fine-tune the controller for optimal performance. With proper tuning, the temperatures remain stable that way.
So here we see our dashboard, and here we can hear the temperature readings, and the OD measurements will appear. In the temperature section, here we can adjust the temperature, the PID target, and this will actually appear here in the AWS server. This is subscribing to the ESP32 input, and it's actually being published in our code here, ESP32 input. And this basically microcontroller is also listening to this.
The way the input is received by the nanoboard is we use the MQTT configuration, where we write in the server for our AWS, we write in the topics for our subscription and our publication. And then we, in this case, we decode the message that's being sent. So then we store it in the received message. So the message being sent comes from us subscribing to the topic of subscription. And this means that we'll be listening for any inputs that come from our dashboard and from us changing the temperature slider, for instance. The way this happens is the target temp, we set that equal to the received message payload. And then this target temp is then used inside of our PID controller. And therefore, this is barely able to change with the website. We also ensure to save all the data locally using a log file, saving it as a TXT, and taking the average temperature of samples and saving this so that it can run locally and save the data locally.